So let's get right to lectures 3 and 4. That's going to be chapter 2. So last time we talked about a few things here. We talked about, I showed you how I will write some of these common variables that you're going to encounter. I'm starting a running list here, which I would suggest you do the same thing, starting a running list on another sheet somewhere. Just kind of keep to the side. And we talked about volume, we talked about pressure, and we talked about temperature, capital T temperature. So those are some of the main things we talked about. We introduced, some of you probably have never seen the concept of specific volume. That is a lowercase v, so total volume, of course, is capital V with a cross on it. When I write it out by hand, that's how I know that this is not speed. It's a capital V with a cross on it. Specific volume is volume per unit mass. That's an intensive property. It does not depend on the extent of the system. It is not an extensive property. Specific volume is the reciprocal of density. Okay. Let's see what else. So we talked, like I said, we talked about volume, specific volume, we talked about pressure, and we talked about temperature. Okay, so those are kind of the main things. We pretty well tied up chapter 1. There was also the idea of a system. If you don't know the definition of a system, be sure and go back and look in your notes. That is important. That's going to be important throughout the semester. There are two types of systems. And if that doesn't immediately come to mind, that's okay. It's brand new information. What I might suggest is pause, go back to your notes, and tell me what is a system and what are the two types of systems. Go ahead and pause now. Okay, so hopefully you know what a system is and you know the two types of systems and what is the difference between the two. I'm not going to write that here. We've already talked about that. That is important. You need to know that. So let's keep moving, shall we? So, sorry, let me put my phone on. Well, I hate to put it on silent because I want my timer to come through. I'm going to get a lot of dings there. I apologize. Let's keep moving, shall we? We did introduce this concept that in a column of fluid, we have this expression that the change in pressure is equal to the density of the fluid times gravity times Z1 minus Z2 if we assume that Z is referring to elevation. That's Z increasing in the up direction. Now, a lot of texts will say delta P is equal to rho G delta Z, and that's okay if you're assuming Z is referring to depth. So as you move down in the fluid, as you increase your depth in the fluid, we should experience an increase in pressure. As we move up in the fluid, as we increase our elevation, we should experience a decrease in pressure. So it depends on what you call Z as to which way you write this, but we're still talking about the same idea. We're saying that as I change my location, if I change my elevation within a column of fluid, or change my depth within a column of fluid, I will see a change in pressure proportional to the weight of the fluid above me. Okay. And we finished it up with a discussion of a manometer, and I kind of set up some very simple examples for you. There are some in the text there. So a manometer is a device used to measure pressure with the height of a column of fluid. Okay, so if you have questions on the homework or something's not clear, shoot me an email and let's see if we can kind of point you in the right direction. Feel free to take a picture of something that you're not sure what's going on, a problem in your book, or not sure how you get to this solution, or whatever the case may be. Send me a picture of your work. Just email it to me, and I can send you an email back, or we can set up a Zoom session or something, and we'll try to get your questions answered. That's no problem at all. Okay. All right, so we will work some examples. I'm going to try to keep these videos from going too long today. So let's work some energy examples. So our focus today is going to be for lectures 3 and 4. Our focus would be for chapter 2. So normally in a face-to-face class, I would do chapter 2 basically in 2 lectures, lecture 3 and 4. and that's what we're going to put together a set of videos to kind of replicate that today. So, Chapter 2 in your text, in the Changle and Bowles text, Chapter 2 is an introduction to the first law of thermodynamics. As we mentioned last time, the first law of thermodynamics is the conservation of energy principle. So, if we're going to talk about energy and conservation of energy, we need to make sure we understand what is energy. Well, energy can take a number of forms, but it's one of the best definitions I've seen for energy. I'm going to set this aside so I don't push on it. What is energy? Well, this is one of my favorite definitions of energy. It is a quantity which can influence the temperature, phase, and or motion of matter. So, I have a cup of water here. As I normally do, as we discussed, I tend to get I tend to lose my voice when I talk for an hour or more, and for these videos I'm going to be talking about 2 hours straight at least. Excuse me, so I keep water there. Just try to keep my throat hydrated, my voice hydrated. Now, I mention that because I could take this water and I can add energy to this. I'm adding energy to it right now. Right? I'm sloshing it around. That's adding energy to it. My hand is applying a force to the cup, and that force is being applied through a distance back and forth, and that's adding work to the fluid, and that's causing kinetic energy of that fluid. So I can change the motion of that fluid by adding energy that way. I could also take a fire. I could take this and set this over a fire, or just holding it in my hand. I'm going to be adding heat to this liquid. If I put it on the stove and I heat it up a lot, and if I got to a point where I put so much in it begins to boil, then I could change the phase of that water. Or if I put it in the freezer, I could remove so much energy I'd change the phase of the water and get it to ice, or I'd boil it off to steam. All of that is done through energy, various forms of energy. So different types of energy will influence matter in different ways. And that's what the first law accounts for, all of that energy. The second law, as we mentioned last time, kind of controls or limits what we can and can't do with energy. But the first law just says one thing you can't do is create new energy or destroy existing energy. It has to go somewhere. And the things that it can do is it can change the temperature, the phase, and or the motion of the material that you're either adding energy to or removing energy from. That's essentially what the first law boils down to. Now, how do we measure energy? We've talked about dimensions and units. What are dimensions and units? And that's one of those things I said, hey, go look this up. So hopefully you have a grasp on that. One particular unit we talked about last time was the pound force. That's not going to work. So there is a subscript F in here, pound force. I don't think my stylus is going to get any better. If there is no subscript on an LB, I need to get a stylus that works. If there's no subscript on an LB, you can assume it's referring to pound force. In this text, we will deal with pound mass. So normally if there's a pound mass, there will be a subscript of an M on it. In this case, this is pound force. Any unit of force times any unit of distance, in this case, Newton times meter. So any unit of force times any unit of distance will give you a unit of energy. The joule, the standard SI unit of energy, is 1 Newton applied through 1 meter. And most SI units break down kind of on this one-to-one basis. Now, the English or imperial system, that's different. Now, with that said, the British thermal unit, the BTU, that's actually the amount of energy required to raise 1 pound of water 1 degree Fahrenheit or Rankine. So that one actually does have a scientific basis. Most English units don't really seem to have a scientific basis. This one does. 1 BTU is about 778 pound-force feet. It's also just about 1 kilojoule. 1 kilojoule is about 95% of a BTU. Right, so it's not exact, but they're pretty close. So, Google search, inside cover of your textbook has all the conversion factors you will need, and that's, make sure you know where that is and how to get to it. I think I posted a PDF of that in Canvas for you. So, in a closed system, and I've already asked you, hey, what are types of system? Well, here's a giveaway, one type of system. And hopefully you already know why a closed system is a closed system. So if it's a closed system, there's only two ways energy can be transferred to or from that system, and that comes in two forms. That's in the form of heat, which we represent with the letter Q, and work, represented as the letter W. And I said there's two types of system. This is one type of system. There's another type of system, the control volume. Control volume is a system that we allow mass to cross the boundary, as you've already figured out when we paused, right? If mass can cross the boundary, the mass also has its own energy that it brings to the system or removes from the system. So whenever you have mass crossing the boundary, we have to keep track of the energy of that mass as well. But if it's a closed system, we don't have that mass. These are the only two ways energy will cross a closed system. In a control volume, it can be heat, work, and mass, all three. Okay? But in a closed system, we'll start there. Heat and work. Those are the ways energy crosses the boundary. Okay, so this example is in the book in Chengel and Bowles' Thermodynamics and Engineering Approach. And they say they've got a well-sealed, well-insulated room. And what they're saying is that they're saying that if it's well-sealed, that it's a closed system. There's no mass crossing the boundary. And if they say it's well-insulated, right, what this is referring to is if it's well-insulated, they're saying there's no heat. Right, so well-insulated tells us there's no heat transfer. So if we put a fan inside a room, and we say, what does that fan do to the room? If mass can't escape, there's no heat coming in or out, what happens to the temperature inside the room? Does it get cooler or warmer? Well, let's look. What is the system? Right? Well, the system is the room, right? And again, a system is whatever we can isolate from the surroundings. Again, we paused earlier to figure that out. A system kind of boils down to whatever we can draw a dotted line around. Okay, now, so what is the system? And then what is crossing? If the dotted line represents my system boundary, what crosses the boundary? So what crosses the boundary of my system here? Well, you've got electricity coming in right there. Electricity we call work. That's W sub E. That is work done by electricity. Why? Well, electricity is the result of flowing electrons generating a magnetic force. We use that force to basically do work. Right? So it's work because the molecules or the atoms or the particles are all moving in an orderly fashion, all moving kind of in a predictable fashion. So anytime I've got energy transfer occurring that way, whenever there's energy transfer by an applied force, that's work. That's what we have here. We have energy being applied through a force. That's going to be a work term. That's the reason we call electricity work. Now, once it gets inside the room, what does it do? Well, inside the room, this fan motor is going to emit some heat, and it's going to be stirring the air up, which is really just going to increase the overall energy of the air. And that's not a bad place to stop. So we'll pick up the next video from